Okay, gentlemen, welcome to the last week of school. We will just be doing one section this week, which will be heat and changes of state. So we've dealt with heat, raising or lowering the temperature of matter. Uh, so you add heat to something, it warms up, take heat away, it cools down. That seems to make sense, but that's not all heat can do. Heat can also change something's state, but it can't do both at once. So heat can either change something's temperature, raise its temperature, or it can change its state, but it only can do one at a time, so not both. What that means is if we were to look at a graph of some matter, doesn't matter what it is, it could be water, it could be carbon dioxide, it could be anything. Uh, what you would have uh, under the right conditions of pressure, we're assuming the right conditions of pressure. So let's say we have standard conditions of temperature and pressure, and we're doing this for water. What would happen is if you had that water and it was solid, so it was ice, well, if you added heat, what would happen at first is that ice would heat up. The temperature of the ice would heat up, and it would heat up until it reached its melting point. And at that point, as you add more heat, the temperature doesn't change, the state changes. So this would be melting. So you start with solid ice, it melts. Once all of it melts, now you have liquid water. Again, as you add more heat, the temperature will in fact increase. And it will increase up till, if we're talking about water, 100 degrees Celsius, or the boiling point, at which point it will stay constant until all of it has turned to gas. So this would be boiling. From then, once all of it is turned to vapor or gas, its heat could theoretically raise, indefinitely. So again, the heat would raise. And this thing here is called a heat curve. So it just shows what happens to a given substance as you add heat to it, from whatever starting point to whatever ending point. And all heat curves have kind of these 5 lines. They have the 3 states of matter. So this would be solid, liquid, and gas, or vapor if you prefer, and the 2 phase changes, melting and boiling. And the curve for each substance looks slightly different, but it has these same parts. The difference is how big these various lines are, and also where they are. The melting point and boiling point of different substances is different. So the temperature for the melting point for water would be different than the temperature of the melting point for ethanol, alcohol. Same thing for boiling. And also the lines between them, the raising of temperatures, because they have different specific heats and they have different amounts of temperature between boiling and melting, etc. Those will be different too. This graph will take the same basic kind of 5-line stair-step shape, but the lines will be of different sizes for any given substance. But for all substances, this bottom diagonal is a solid, and then you have a horizontal melting, a diagonal where it's liquid, where the temperature is going up, and then boiling, and finally, it's gas. So heat can only either change something's temperature or change its state. It can't do both. So you can have solid ice at 0 degrees Celsius, and you can have liquid water at 0 degrees Celsius. To get that solid ice at 0 degrees Celsius to liquid water, you have to add heat. You actually have to add more heat to make it change state. It's not changing temperature at all. That water, whether it is solid or liquid here, is all at 0 degrees Celsius, and it won't raise up in temperature until all of it becomes liquid. So until the entire sample, the entire piece of matter changes state, it's going to stay at that temperature. That's why we boil, for instance, pasta in water, or we cook pasta in boiling water. So we cook a lot of things in boiling water because it's a very constant temperature that's easy to control. So it allows us to, without having to worry about like getting a thermometer or anything, if you put water to boiling, it's going to be right around 100 degrees Celsius. and you know pretty much no matter where you are what the cooking time for a certain pasta is or whatever. It just makes it really easy because it's a standard sort of condition. So how do we know how much heat we need or how much heat is used? Well, when changing temperature, the equation to figure out how much heat is required or used is Q equals MC delta T. Everything we did last week. Those were all change in temperatures. Uh, they all dealt with a delta T, a change in temperature. Now, you'll note that heat here, Q is in joules. That's going to be important because when changing state, the equation to determine how much heat is used is number of moles times what is called the heat of fusion or the heat of vaporization. And I will explain those in a second. But this is going to be based on number of moles. And also, the heat of fusion or heat of vaporization tends to be given in kilojoules per mole. So up here, when changing temperature, we're dealing with grams and joules. So joules per gram, basically. Joules per gram degree Celsius. Down here, we're going to be dealing with kilojoules per mole. It doesn't mean you can't figure these things out. We can convert between grams and moles and joules and kilojoules. Just be careful when you're working with these to make sure you're using the right units. So, a couple definitions for these two constants. The molar heat of fusion for a substance is the amount it takes to melt 1 mole of a substance at its melting point. And every substance is going to have a different molar heat of fusion. That is something you would look up. I am including online with the worksheet that you're going to get this table, which has a bunch of specific heats and also heats of fusion, as well as a melting point and boiling point for several substances. If it's not on here, or if you'd rather, you could look these things up online, certainly. Just make sure you're looking for kilojoules per mole, because sometimes they'll use some other units other than kilojoules per mole, because industry sometimes uses some other non-standard chemistry units. It should be kilojoules per mole should be the first one you get, though. But again, I think everything on the worksheet is referenced here or actually given to you on the worksheet. But neon, for instance, for 1 mole of neon to go from solid to liquid, it takes 0.33 kilojoules. That happens at negative 249 degrees Celsius, which is pretty cold. So that's the melting point. For one mole of liquid neon to turn into gaseous neon, it takes 1.8 kilojoules. And that happens at negative 246 degrees Celsius. So this thing is liquid for only 3 degrees Celsius, at least at standard pressure. So that's just how you read that. There's a back page here. We won't get to heats of formation or free energy or entropy. So you don't have to worry about that back page. That is stuff we would have done had we had more time. So that will be given to you. So each substance has a different heat of fusion, which is the amount it takes to make 1 mole of a substance to go from solid to liquid at the melting point, and a different heat of vaporization, which is the amount of energy, again, in kilojoules that it takes 1 mole of a liquid to completely vaporize into a gas. There are also technically names for the heats going the other way. So going from a gas to a liquid is technically the heat of condensation. But you don't have to learn that or memorize it or look it up separately. Heat of vaporization and heat of condensation are just equal and opposite. So let's say the heat of vaporization for something is 100 kilojoules per mole. The heat of condensation is negative 100 kilojoules per mole. Because if it takes 100 kilojoules to get it from a liquid to a gas, if you take those 100 kilojoules away from it, it's going to turn back to a liquid. So same thing with solid to liquid. Going from solid to liquid is fusion. And going from liquid back to solid is the heat of solidification. And again, they're just equal and opposite. So you'll usually be given either heat fusion or vaporization, which are the positive numbers, because you always have to put heat in to go from solid to liquid and from liquid to gas. Going the other way, you can just slap a negative sign in front of that number and you're done. But those are technically called the heat of condensation and the heat of solidification. But you don't have to look them up separately. It's just the opposite of the heat of fusion and the heat of vaporization, respectively. So just be aware of that. But equal and opposite, and that kind of makes sense. So what I'm going to do is I'm going to do 2 example problems, and I'm going to show you, I'm going to draw out mini heat curves, kind of like it says on your worksheet too. These don't have to be very specific. They just have to show the shape and kind of show where you are. So I want to kind of give you an example of that. This is one from the PowerPoint. How many grams of ice at 0 degrees Celsius will melt if 2.25 kilojoules of heat are added? So the first thing I'm going to do, and the first thing you should do on your worksheet, is draw a little heat curve. And all that means is draw that kind of 5-line stair-step thing. It does not have to be to scale or right or anything. But what you want to do, and how this helps, or at least how I think it helps or could help, is it keeps straight what you are doing as far as where you are and which equations to use. So we want to melt ice. So we want to go from solid ice to liquid ice, or from melt ice, from solid water to liquid water at 0 degrees Celsius. So we're starting with solid at 0 degrees Celsius, which would be right at the beginning of the melting phase, and we're ending with a liquid. And that just tells you kind of what you'll be doing. We will be using the heat of fusion, because if I were to go back to here, these things all correspond to different things. So if we're over here with delta H fusion, which corresponds to the amount it takes for melting, and this would be delta H vaporization. And then all of these would be, let's see, Q equals MC delta T, Q equals MC delta T, and Q equals MC delta T. If on the diagonals, the temperature is changing, so you're just using Q equals MC delta T. But for the state changes, you have to use the heat of fusion or heat of vaporization, and you just multiply that by the number of moles. So back to where we were. In this case, I need to use the heat of fusion. So what we want to find out, so N times delta H fusion equals Q or delta H. Remember, Q and delta H for our purposes are the same thing. And in this case, we actually want to figure out N, because it's asking how many grams, and we have to get that through number of moles. So rearranging for N, which isn't hard to do, N equals Q divided by delta H fusion. I just divide both sides by the heat of fusion, and I can plug all those numbers in now. N equals Q, which is 2.25 kilojoules. And we can leave it in kilojoules here because, and we should leave it in kilojoules here, because you'll see at the top, I put that the heat of fusion is 6.01 kilojoules per mole. If you look, the kilojoules will cancel out. You'll end up with moles, which is what you want. So all I have to do for that is 2.25 divided by 6.01. And you find out you get N equals 0.374 moles, 3 sig figs there. And then put that over 1, 18.02 moles of H2O to, grams of H2O to 1 mole, sorry. One mole H2O, that one looks terrible. And that'll give you the number of moles. So 0.374 times 18.02 tells us we end up with 6.74 grams of water. So 6.74 grams of that ice will have melted into water. And it doesn't matter how much ice we have. If we add that much heat to it, assuming it's right at 0 degrees Celsius, 6.74 grams of it will melt. Okay, so the last example I'm going to do is going to be a little more complicated. It's going to involve 2 steps. So how much heat would be required to melt 45 grams of ice at 0 degrees Celsius, and then heat the water to 70 degrees Celsius. So again, I'm going to draw my little mini, not to scale at all, just sketch of a heat curve. So that would look like this, with the 3 states as diagonal lines and the 2 state changes as horizontal lines. And in this case, I'm starting with ice at 0 degrees Celsius, solid ice, which would be right there, right at the beginning of the state change. And I'm going to heat the water. I'm going to melt the ice and heat the water to 70 degrees Celsius. Well, 70 degrees Celsius is up here, right? It's almost to the boiling point of water, not quite. So what you have to understand is each segment of the heating curve has its own equation or its own step associated with it. And as I showed you on the first one I did, this would be this step, so step 1, which would be melting. That is a terrible L. Would be N, number of moles, times delta H, fusion in this case. And step 2, which would be heating, is going to be Q equals MC delta T. If temperature is changing, we're just using the Q equals MC delta T that we've used. So if you want to know how much energy it is to melt the ice and then heat it, you have to do it in 2 steps and then add those numbers back together. So we'll get number of joules out of each of these, and we'll add them back together for a total. So in step 1, it's N times delta H fusion. So first we need to figure out how many moles we have. 45.0 grams H2O over 1. And then we would do that as 18.02 grams water, 1 mole of H2O. And now I'm going to show you a way to just add this into the dimensional analysis. I told you can use this dimensional analysis method for a whole bunch of stuff, and we've been using it for some things. I like to just keep using it because it makes everything organized, and it takes up less space when you're writing it out. So I'm going to plug this in here. I happen to know, and again, this is from the last page, but the delta H fusion for H2O equals 6.01 kilojoules per mole. So I happen to know that because I had it on the previous page. I've looked it up. That's one of those numbers I have burned in my brain that I'll never be able to get out of there, even when I can't remember my kids' names anymore. So, that'll always be there. But that is actually a conversion factor between kilojoules and moles. It's weird to think about, but it's kilojoules per moles, right? So 6.01 kilojoules per 1 mole once I convert to moles. And if you look, grams will cross out, moles will cross out. I'll end up with kilojoules. So you can use dimensional analysis for that. So now it's just a matter of doing the math. And if I do the math, I get 15.0 kilojoules. I go to 3 sig figs, and it's actually 15.00. So rounded to 3 sig figs, 15.0. So that's for step 1. So this first part right here, that takes 15 kilojoules, getting from solid to liquid. So step 2, the heating phase, we can figure that one out too. Step 2 will be Q equals MC delta T. So Q equals 45 grams of water that's M times the specific heat of water, which is, I hope you guys know by now. And again, you can always look this up, but it's 4.18. We did a lot of calorimetry, so 4.18 joules per grams degrees Celsius. Important here that it's joules and not kilojoules, because when we combine these again, we're going to have to convert either the first one to kilojoules or the second one to joules. But you can't add kilojoules and joules and get like a sensible answer. So 45 grams times 4.18 joules per gram degrees Celsius times the delta T. And in this case, we're going from 0 degrees Celsius the water here would be 0 degrees Celsius and going to 70 degrees Celsius. So, you know, I'm going to call the delta T 70 degrees Celsius because that's how much it raised. Hopefully that isn't too confusing to anyone. And so if we do that, so if you do the math on that, 45 times 4.18 times 70, you get 13,167 joules, but rounding to 3 sig figs, that is 13.2 joules. And then you'll see right here, I converted that to kilojoules. The reason I converted that to kilojoules is it asks the total heat required. So step 3 here is just total all steps. And to do that, you need to put everything into joules or kilojoules. Either one is right. I don't remember on the worksheet. Just be aware some of the bottom answers might be in joules instead of kilojoules or vice versa. As long as you have the right unit with the right number, either answer is acceptable. So I'm doing kilojoules because it's less writing and I'm lazy. So here we have 15.0 kilojoules plus 13.2 kilojoules, and that's going to equal 28.2 kilojoules. So if you have 45 grams of ice at 0 degrees Celsius and you add 28.2 kilojoules to it, you will end up with 45 grams of water, or 45 milliliters of water, at 70 degrees Celsius. So each segment is going to have its own equation. So if you're going over more than one segment, in other words, you're going on a horizontal and a diagonal, you have to split them up into separate equations. And yes, theoretically, I could ask you to do, and I will do an example of this, where you go from solid all the way to gas and then raise its temperature, and you have to do 5 equations and add them all together. It's not hard, it's just a lot of work. So that is a brief overview of kind of energy in states of matter and heat curves. Tomorrow, you'll watch a crash course, and then I will do on Wednesday some examples from the homework. I'll just write out a couple examples, and maybe I'll do a big heat curve that I make up, more complex one, and that's it. So that'll be it for the week. Your homework's due on Thursday. So, gentlemen, have a good week.